Welcome to Brain Vision.
So it's saying to find the the specific heat capacity at constant volume. So we have the molar mass of H2O. This is going to be equal to 0.018 kilograms per mole. And then they're telling us disregard vibrational motion, and we have 3 rotational degrees of freedom, 3 translational degrees of freedom, so we have 6 degrees of freedom. And the molar specific heat capacity at constant volume is going to be degrees of freedom times R over 2. This is going to be 6R over 2, or simply 3R. We can find the specific heat capacity. So the specific heat capacity would simply be equal to the molar heat capacity divided by the molar mass. So this would be equal to 3R over m, or 3 times 8.314 over the molar mass of 0.018. This is going to be equal to 1,385, and then the unit for specific heat would be joules per Kelvin, per kilogram per Kelvin. And then they're saying, okay, the calculated, the real specific, we'll say actual, is actually 2,000. So what does that say about what does that say about vibrational motion? What does that say about vibrational motion? Vibrational motion has a large influence in complex molecules. So vibrational motion has a large influence in more complex molecules, such as triatomic molecules, such as water. So we solved it. We solved for the specific heat capacity at constant volume. However, it's much less than, it's on the same order of magnitude. However, it's much less than the actual specific heat capacity. And that's because, again, vibrational motion has a large influence in these more complex molecules. And a simple approximation like this is not sufficient enough in order to obtain the specific heat capacity at constant volume. And that's the end of the solution. Thank you for watching.